start also. There we go. All right. So streaming is on, and I'm confirming it on my own browser, like now. Not seeing anything. Okay, there we go. All right, so streaming is on. Live screen share is on, and live streaming is on too. Yep, YouTube should be on. And I think some kind of setting is changed because I usually do not get sound effects when people join the the voice channel, and now it's making interesting sounds, much more interesting than before. Oh, you guys cannot hear me? I'm pretty sure I am talking on both YouTube and also on Discord. So can you guys hear me? Sounds like a commercial. Okay, cool. All right, excellent. So I'm going to get started with the practice exam. And we can talk about the A-star algorithm too, but I think the exam is a little bit more important. I think question number 2 may answer some of the questions that some of you may have. So I'm going to get started here, starting with question number 1. So question number 1 and question number 3 are kind of related, even though they are in some way opposites of each other. So we'll deal with question number 1 first. Question number 1 says Jackie has a coin purse that only has trick coins of 2 types. There are exactly 2 coins that are loaded to land on a head with a probability of 0.6. There are 7 of the other types of coins which has a probability of landing on a head of 0.35. In a game, Jackie randomly picked 4 coins out of the coin purse. Jackie then flips each picked coin once. What are the chances that exactly 2 picked and flipped coins land on heads? Alright, so that's the question. So does everybody understand the configuration of the question? If there are any confusion about how it is configured, we should talk about that first. So let me ask you this question. How many coins are there? How many total coins are there in the purse? That's the first question. Yep, exactly. So there are 9 coins, and of the 9 coins, 2 are the ones that will have a chance to land on the head with a 0.6 probability, and then the other ones, the other 7, would land on head with a probability of 0.35. Yep, there you go. So Armand is correct. Okay, so how do we start with this problem here? So the first thing we do is we deal with what kind of coins are we gonna pick up from the coin purse? How many different ways can we pick up coins from the coin purse? That's the first question. So we have to figure out how many out of if we are to pick 4 coins, there are like 5 different possibilities, right? Well, let's see. No. There are, let's see, none, 0, or 1. So there are 3 possibilities when we pick 4 coins out of the coin purse. So I'm gonna start with writing this in. I could do it in Joplin. There we go. So I'll just kind of write down the configuration. This is for question number 1. So we have 9 coins, 7 with a probability of the head being 0.35, and then 2 with a probability of landing on the head with a probability of 0.6. Okay, so there we go. We have 2 different coins. We know how many each one we have. So we are going to draw 4 coins without replacement. All right. So how do we know it is without replacement? So randomly pick 4 coins out of the coin purse. So if you have any question like this, are we putting the same coin back into the purse? You should probably ask that during the exam. Yeah, because I would answer those questions. Okay, I would just go like, okay, once you take a coin out of the purse, you do not put it back in, in the same experiment. Now and then what we'll do is we flip each picked coin once. Okay, but that part comes later. So now we have to figure out the 4 ways of picking the coins. Okay, so the first one is I'm gonna have to start to label these different coins. So I will just say okay, I will just use the probability as the label. So we have only 2 of the ones that can that have a chance of landing on the head with a chance of 60%. So we can have 2 of both of those, and then the other 2 would be the other kind, and then we can have only 1 of those, and then the other 3 would be of the other kind, and then we can have 0 of the 0.6 ones, and then everything that we picked from the purse are the 0.35 types. So these are the 3 combinations that would make sense to us. Do we have any questions about why we have these 3 combinations of coins? Right, so at this point, order does not matter. Order does not matter in this case. Because what we want to do, what we want to figure out, okay? So the reason why order is not important is because in the end, we just want to figure out what are the chances that exactly 2 picked and flipped coins land on heads. So that particular question, this last part here, does not say anything about, but we only care when it is the first flip and the last flip that landed on the head. Nope, we just say when exactly 2 picked and flipped coins land on the heads. So if that portion is order independent, we don't care about the ordering, then the way we choose the coins, is not going to be important either. We just want to know, out of the coins that we have chosen, which ones, how many of those have a probability of 0.6 and how many of those have a probability of 0.35. Alright, so now we do want to figure out if we are to pick 4 coins out of it, okay, how many times, what is the relative probability of getting this, and what is the relative probability of getting this, and what is the relative probability of getting this. Okay, so we do want to find that out, and we also want to find out what is the omega. Okay, so in this case, what is omega? Can somebody try to work out what is the cardinality of omega? We don't really care about the actual set of omega. We just want to find out what is the cardinality of this omega here. So what would that be? In other words, how many coins do we have, right? Of those coins, we have 7 of one kind and 2 of the other kinds, and we want to figure out, what are the relative probabilities of these, or I should say, how many ways can we choose coins out of 4 coins out of 9? Nope. The omega cardinality of omega is definitely not 4. It should be quite a bit more than that, because we have 9 coins, right? So even if ordering is not important, we have 9 coins to choose from, but we are only choosing 4 out of those 9. Alright, so let me give you a trick here. Okay, so instead of looking at the 7 coins of one type as one category, you might want to label each one as A, B, C, D, E, F, G. Okay, and then the 2 of the other kind, we label those 2 as X, one as X and the other one as Y. Because as far as how we choose those things out of 9, each one is unique. Each one is its own coin. So okay, so I think some of you are already starting to get to the solution here. Shall I, give you guys the answer, or you guys want some more time? Okay, I'll give you guys some more time. So look at those 9 coins as 9 coins, each one has an ID on it. Even though 7 of those have the same probability of landing on the head, and then the other 2 have the same probability of landing on the head, you still want to consider those 9 coins as unique coins when we are just looking at the omega, which is the cardinality of all the possible outcomes. And where is that 126 coming from? So what is the equation? What is the formula that you use to compute the 126? That would be correct. So we are choosing 4 out of 9. That is correct. Okay, so I'm just going to throw this in. Okay, we have 9, choose 4. It didn't work before. Oh, okay, it does work now. Okay, very good. All right, so that is 126. Alrighty, very good. So now what we need to do is to say, what about the cardinality? Oh, okay. All right, so now we have to figure out each individual one. Okay, so for this one, how many, what would be the cardinality, okay, of doing something like this? So now what you need to do is to think about, okay, we need both of the ones, so now you need to separate the two into 2 categories, right? Because you need 2 of the first category and then you need 2 of the second category. There are only a total of 2 of the first category, so you're going to say, we need both of them. And then for the other category, there are 7 of them, but of the 7, you just need to get 2 of them, right? So if we want to look at the cardinality of something that looks like this, what would be the number of ways to choose coins out of the purse? And we end up with 2 coins having 0.6 and then 2 coins having 0.35 as the probability of landing on the head. This one is really kind of, it should have a lot of resemblance to the, what is it again? The lottery. Yeah, the lotto problem. That's it. Alright, so I'm just going to say here, okay, the number of combinations in this case is 2 combinations. The first one is 2 choose 2 because we have 2 types, 2 of the kind that has a probability of landing on the head of 0.6, and then for the other one it's going to be 7 choose 2. So now we have 7 choose 2 and backslash for the choose. There we go. And then for this kind we have 2 choose 1 and then 7 choose 3. Oops. Not pound, we need dollar. There we go. So we have 2 choose 1 and then 7 choose 3. And then for the last category, we are looking at 2 choose 0 and 7 choose 4. So 2 choose 0 and then 7 choose 4. There we go. Yes, 7 is coming from, we have a total of 7 coins that have a probability of landing on the head at, with a 0.35 probability. Alright, so now the question is, but Tech, you earlier mentioned, well, I forgot the word, but Jonathan reminded me of the word. So Tech, earlier you kind of mentioned that this has something to do with the lotto problem. Well, that's because with the lotto problem, you have 2 different types of numbers, the lucky numbers and the non-lucky numbers. Of the 68 numbers, 5 are lucky numbers because those are the 5 chosen by the game, and then the other 64 numbers are not the lucky numbers. So when you try to analyze how many ways can we print lotto tickets of a particular price level, we basically take into consideration of, okay, so how many of the lucky numbers do you want to choose and put it onto this ticket, and how many, and then the rest have to come in from the non-lucky numbers. So that's where we first saw this type of counting. Okay, this type of technique of counting. All right. So now that we know how many ways we can do a certain thing, as it turns out, this omega turns out to be not really that useful, because our probability is limited to just picking 4 coins out of these out of the 9. So this number here, the 126, is not terribly helpful to us. But it does give us a sense. It gives us a sense of what these numbers should be. Because if you end up with like 600 something for one of these numbers, you know that it cannot be the case, because there are only 126 ways of choosing 4 coins out of 9 to begin with. So all of these numbers need to be significantly less than 126. All right. So we got the first portion of the question answered now. Okay, and then we are gonna tackle the second part of the question, but I'm gonna let Armand finish his typing first. All right. No, these are multiplications. So these are multiplications because because of the 4 coins, you have 2 coming from the 0.6 and 2 coming from the 0.35. So the number of ways you can get 2 out of the 2.6 needs to be multiplied with the number of ways you can choose 2 out of the 0.35s. So these are multiplications and not additions. You can also think about this, from the perspective of a tree. So, if you look at it as a tree, every time you pick something, you are branching out, right? So that kind of shows you, after the first 2 levels of the tree, which represents, how you choose the 2 coins with a 0.6 probability of landing on the head, then each branch after the first 2 levels of the tree, each branch is representing, how you can choose 1 coin from the other type. So that's why it is a multiplication and not an addition. Yes, so they are okay, so it depends on how you look at it. You can look at these as you can look at these as 2 separate experiments, whereas the first experiment is to choose 2 out of 2, and then the second experiment is to choose 2 out of the 7, but they are independent. So for each way of choosing 2 out of the 2, you have to be able to combine that with one of the 2 choosing 2 out of the 7. So that's why it is a multiplication. Jonathan is correct. If you add up these 3 numbers, they should add up to 126, because this should exhaustively be all the ways to choose 4 coins out of the configuration that we have. That is correct. I said multiplication. Oh, okay. So I misunderstood Aman's question, because I thought Aman was asking, is there a hidden plus operator here? And the operator should be a multiplication, not a plus. So I misunderstood the question. Sorry about that. Oh, okay. Oh, okay. So I did not misunderstand. Okay. Yeah, so between the choose, it is a multiplication. So if I want to make it very clear, that is a dot in between those 2. But if you add up the 3 numbers, then you should end up with 126, because that should account for all the different ways to choose 4 coins out of 9 in this case. So we should end up with 126. If you add this product and this product and this product, we should still end up with 126. So Jonathan is correct about that part. So if I were to give, okay, let's make this super duper clear. Okay, so we'll give these things names, right? So this is A, and this is B. Whoops. B equals 2, and then this is C equals 2. So 128, this should equal to A plus B plus C, which is 126. Is that more clear? Which number I'm adding to which number, and it should end up with which number? Okay. Yeah, sure. Absolutely. Excellent. All right. So that addresses one part of the question. Okay. The second part of the question is really looking at each way. Okay, let's say we have two coins of the 0.6 variety and two of the 0.35 variety. So now the question is, given these are the coins that we have, what is the probability of landing two heads and two tails? Given these are the coins that we end up with. And then for the second one, same question. Okay, and then for the last one, same question. So the last one is the easiest because all the coins have exactly the same probability. So for the last one, okay, so if you want to focus on this one first, so I'm going to use a subpoint over here. So we'll say you will have to multiply the 4 picked coins probability by the other probability we are finding. Okay, so this part has to do with binomial distribution. So the way we figure out these numbers here, that has to do with just regular counting, having experiments without replacement, that's combination, where ordering is not important. So now with the subpoint here, we are looking at binomial distribution. So now we need to look at binomial distribution. So in binomial distribution, this one is the easiest one because all the coins have exactly the same probability. So in this case, each event is independent. Yes, so each coin flipped is indeed independent. In fact, we have 4 different coins, so we are not even tossing the same coin 4 times. We're tossing one coin once, and we want to find out what is the probability of exactly 2 coins landing on the head and the other 2 landing on the tail. So that's what we are asking. Each coin doesn't have the same probability for heads. Now these 4 does, okay, because for this particular subcase, we are handling the case where we have 4 coins and each one is landing on the head with a probability of 0.35. So this is the easy one because they all have the same probability. Okay, so now what we need to do is simply to say we have 4 to choose 2. Okay, so let me use equation mode here. So now we have 4 choose 2 because that's exactly what we have. We have 4 coins. They all have the same probability of landing on the head. And then according to binomial distribution, this is how we do the calculation. So we have 4 choose 2 and then times 0.35 to the power of 2. Those are the 2 landing on the head. And then times 0.35, 1 minus 0.35, which is the chances of landing on the tail, also times to the power of 2. So just kind of focus on the right hand side here because that's the finished equation. So this is the probability, okay, of each one of these tosses. It will be the probability. This is the probability. So we have to multiply this to make a weighted item, to make a weighted entry that we will add up at the end. So let me just make it very clear what this number is. Okay, so we'll say for each experiment of flipping each coin once, the probability of having 2 coins landing on their heads is that. There we go. So let me fix the typo here. There we go. So the problem is asking for exactly 2. That is correct, and this is exactly 2 for this kind of configuration. So are we good so far? So I'm just handling the easiest case first, and then we'll handle the other 2 cases where it is they're just tedious. Okay, they're not really more difficult. They're just kind of tedious. All right, so assuming that the answer is yes, we are going to move on to the next one. All right, this is the messy one, or messier one. The first one is actually even messier. Okay, that's because with this one, we have one coin that is different from the other three. So now it is possible that one head goes to the 0.6 and then one head goes to the one of the 0.35s. Or we can have 0 heads from the 0.6 and both heads are contributed by the 0.35. So now we have two sub cases to handle in this case. All right, so what is that going to look like, right? So the way it's going to look like is we have two components. Okay, so I'm going to use equations here. We have two components. The first component is simply to say, of the one coin that has a 0.6 chance of landing on the head, we end up with a tail with that one. Okay, so that means the count, because when you're dealing with binomial distribution, you always have a count. So in this case, we are saying, of the one, we are choosing 0 because none of the coins, or the only coin with a probability of landing on the head, is landing on the head. So, but if it is not landing on the head, it has to be landing on the tail, and the probability of that happening is 1 minus 0.6, which is 0.4, to the power of 1. So we first have that component, and then the second component is coming from the 3 coins that has a chance of 0.35 landing on the head. But this time, we know both heads are contributed by two of those 3 coins. So now so first we have to do the counting. This is binomial distribution again. So this time we have 3 choose 2 because of the 3 coins that has a chance of landing on the head with a probability of 0.35. 2 of them did. Okay, so now we say 0.35 to the power of 2. Oops, to the power of 2. And then we also have to handle the one case where it did not land on the head, so it's 1 minus 0.35. That's the chances of landing on the tail, and this time it is to the power of 1. So are we doing okay so far with this one? It's a little tedious because we had a little confused. All right, so okay, I can go a little bit slower. Sure. All right, so that's one. Okay, so the other one. Okay, so I'm just going to copy and paste the equations. I know that is not a way to go slower, but I will explain it as I make changes to the equation. Come on, it's not cooperating. Okay, there we go. Nope. It just pasted whatever is in the buffer. Okay, let me see if I know. Okay, because I turn on the VI key binding, so it's just using the VI thing. Okay, so I'm changing this 0 to a 1 because this on the second sub item, I'm accounting for the fact that one of the 2 heads is contributed by the 0.6 and the one is contributed by the 0.35. So there's one coming from the 0.6, and we also have to change there's only one this time coming from the 0.35, and as a result the power has to be changed because for those 3 the chance of landing on the head is 0.35, and then the chances of landing on the tail is 1 minus 0.35. So now we have to add these 2 numbers together. So I'm just going to pause here until you guys say it's ready to go, then I'll continue. No, these 2 are going to be added. These 2 need to be added because they belong to the same subcase over here. Yep. Okay. All right. So this one is just uglier, okay? But basically the same thing, it's just uglier. So the reason why it's uglier is because now we have 3 subcases instead of 2. So I'm gonna just kind of paste 3 times here, because this time we have 2 of the 0.6 to consider. So with 2 we can have 0 of the 2, we can have 1 of the 2, we can have 2 of the 2. And then the other also only has 2. So we have 2, 2, and 2 over here. But this time, the other number has to compensate for the first one. In other words, when we add how many we are choosing, the sum has to add up to 2. So if we have 0 of the 0.6, then we have to have 2 of the 0.35. If we have 1 of the 0.6, then we have to have 1 of the 0.35. And if we have 2 of the 0.6, then we have to have 0 of the 0.35. Now obviously the power also has to change, because the power has to do with the we have 2 components of the power. One is for the heads and one is for the tail. So this time, it does get a little bit uglier. Oh, you know what? I made a mistake over here too. Sorry about that. I did make a mistake here, because this time I have to say not 1 minus 0.6, but it really is just 0.6 to the power of 1, because that is corresponding to landing on the head. Okay, so for these ones, we have to generalize and just it just makes it kind of uglier. Okay, so because we have 0.6, 0.6, 0.6, these are the chances of landing on the head. And then you have to raise the chances of landing on the head with the actual number of landing on the head, which in this case is 0, and in this case it is 1, and in this case it is 2. And then the chances of landing on the tail is exactly 2 minus the number of times that it would land on the head. So this would have a 2, this has a 1, and then this now has a 0. Okay, so for the second one you can write yeah, exactly. So for this one, if you want to kind of make it more general, you can always have a 0.6 to the power of 0 over here, and then here you have 1 minus 0.6 to the power of 0. I mean, it does make sense, because you want to make sure that you understand how the general equation works. So now we're going to get onto this side and kind of make the same kind of changes. So we have 2 out of 2 landing on the tail, so none is landing on the head, both are landing on the tail. And then this one we have 1 landing on the head and 1 landing on the tail. And then for this one we have 2 landing on the head and 0 landing on the tail. And now we got the right numbers, or the other way around. Oh, the other way around. Darn it. Okay. So we have 0. I just flipped the order. Okay, 2, and then we have 0, 1, 2. There we go. All right. So if you just look at the right hand side, it's a lot easier to read. All right. So are we okay so far? I mean, just breaking up, how these things can go, all the subcases. You wouldn't think it is that complex, right? I mean, you just have a little purse, a little coin purse, and then you have 2 types of trick coins in the purse, and you just go like, okay, I'm just gonna randomly pick 4 coins out of the purse, flip each one once, and then I'm just asking, what are the chances that I would have 2 coins landing on the head and 2 coins landing on the tail? I mean, how can it possibly be this complex, right? So what is the answer? The numerical answer is to add up these 3 numbers, these 2, and then this 1, and just add them all up, and there you go. That would be your actual probability of having exactly 2 coins landing on the head of the 4 that you choose out of the purse. Yeah, just add up all these. So okay, so if I were to just give him I mean, how do we do things like at least 2? Okay, so if I say at least 2, it means 2, 3, 4, and whatever the upper limit is. So all of those are cases that you need to consider when we say at least 2. Or if I say up to 2, that means 2 is one case, 1 is one case, 0 is also one case. So they should all be considered, each one should be considered separately when we say words like at least 2 or at the most 2. Yeah, exactly. So you have to break each one into its own case, especially in this case because each one is representing a different number of coins of each type, and that's why they have to be considered in its own way. Alright, so Ahmad asked, don't you need to multiply the flipping of the coins by the probability of choosing those coins in the first place? Yes. So he is correct because we have to multiply this number by the sum of these three numbers, multiply this number, which is the count, by the sum of these two, and then multiply this number by this number here, and then we add up all those products together. That will be the final answer. So yes, Aman, you are correct. I forgot about the count of ways, the number of ways to come up with those coins to begin with. Yes. Yep, you're right. So the way this is going to be graded is, I will basically be looking at the reasoning. So I'll be looking for the reasoning of the counting of each combination. So there are 3 different ways, right? This is 1, this is 1, and then this is 1. And then for each way, I'm looking looking at all the chances, okay, of having 2 coins, both contributed by the 0.6, 1 contributed by the 0.6, 1 contributed by the 0.35. And what I'm really looking at is, do you know when to use binomial distribution, and do you know when to use the lotto kind of distribution? But it's really just counting in that case, counting the number of combinations. And do you know how to combine those two into one? So this question is a combination of, no pun intended, it's a combination of of combinations and binomial distribution, and kind of all rolled into a problem that seemed to be pretty easy to solve, because it seems pretty easy, right? Just 9 coins in the purse. How hard can it be? Well, as it turns out, there are a lot of subcases. So that's for question number 1. Okay, so the practice part has to do with separating the steps and understanding which step needs to use the lotto technique, and which steps has to use the binomial distribution. So you have to kind of look at the problem and be able to separate it into 2 different steps, because with this problem, the first step is really choosing the 4 coins out of the purse, and then the second step is to flip each coin once and see what are the chances that you have both at exactly 2 coins landing on the head. So that separation is the key, okay? And in order to make that separation, you have to be familiar with both ways of computing probabilities. In other words, you have to be able to recognize when to use the lotto technique and when to use the binomial distribution technique. Have to multiply by probability of choosing the scenario of flipping in the first place. Yes. Yep. Yep. Alrighty. So are we ready to move on to question number 2, which is also, by the way, interesting, very interesting on its own. I hope some of you had a chance to kind of read the questions over the weekend. Oh, okay. Yeah, okay. So for question number 2, it might be harder to read because the first time I asked questions like that, I was people did not know what I was asking, so I was trying to be more verbose this time, and obviously that didn't actually work out. Okay, yeah, go get some water. I'm not taking row anymore, by the way, so no need to worry about me taking row when people need to go to the bathroom or get some water. Okay, cool. All right, so this is question number 2. So question number 2 is interesting because I have to think of ways to ask questions where I can generate a variety of things, but at the same time, I will be able to see whether people understand the algorithm in this case or not. Okay, so in this case, I even give you a link to the module. So in the exam, you can just click on this link and read the module itself, or at least have access to the algorithm in the module itself. So what is given to you? So I'm going to read the other part later on. So what is given to you is the update of stuff as we run the algorithm. So we basically confirmed what is in the O set. This is for A star algorithm. We will then say, okay, for whatever strange reason, we choose V1 as variable C in this case, and once V1 is removed from the set O becomes empty. And then we evaluate all. Now this is the A star algorithm, so we have to look at outgoing edges from whatever vertex we have chosen from O. So we look at the first edge as V1, V3, and then the value of local variable t is updated to 5. Now, you kind of have to look at the algorithm itself to find out why it is 5, right? Because there's a reason why t has a value of 5. It has to do with how the algorithm is computing the value of t. So now we have the indentation indicates nesting. So we have one more level of indentation here, which means the condition of the conditional statement is true. That's why we are updating O, the G value, the F value, and also the previous value of V3. So you're looking at a trace of running the algorithm on a specific graph. I'm not giving you the graph. So your job is to recreate the graph and also the values of the various things that you need to figure out in the graph, such as the distances of the edges, the connectivity between the vertices, and in this case, possibly the heuristic value. Now, certain things have a kind of question mark here, because I do not want to give you the answer. Okay, so that's why there's certain things that are kind of like, is it called redacted? When you block out something from a confidential document. Redacted. That's it. So I'm using the same technique here to redact certain things, because otherwise it would be way too obvious. So anyway, this is what you're given with, the trace, some of the numbers that you need to work it out, and some of the values are not given to you, such as f of v3 is, I never really give you the exact value of f of v3, but once you read the algorithm, you would know at least what components go into f of v3. Okay, so suddenly SCP. I am not sure how secure copy has anything to do with this, because SCP is secure copy. That's a Linux command line to remotely copy something using the SSH protocol. Yep. But I do not know what SCP means, in this context, what it was meant to be saying. Definitely something else. Okay. All right. So now the question is, how do we approach this? Okay. So it's not about me solving the problem. It is me explaining, how do we proceed to solve this problem. The first one is easy. Okay. If you want to just look at the topology of the graph, in other words, you want to find out where are the edges and potentially, what are the distances of the edges, that is easy to do. Okay, because from all of these things, okay, from V3. So once we have chosen V1, we can see that V1 connects to V3, V1 also connects to V7 in this case, and then V7 connects to V2, and then V2 connects to V4, and then we have V2 connecting to V4, and then we have V4 connecting to V5, and so on. Okay, does everybody understand why I said that? Why, how I was able to say where the edges are? Okay, very good. Okay, I know Jonathan gets it. I think Aman is getting it. Okay, no. Okay, very good. Okay, so when you're not getting it, you need to let me know. Okay. All right. So the question. So now we need to look into the algorithm. And I'm going to open the algorithm in a new window so I can kind of slide it in and slide out, when I need to. So there we go. This is the algorithm. And so I suggest that when you attempt this particular exam, you have a setup where you can open up multiple documents, or know the shortcut keys. Okay, if you know Control Tab can switch between the windows, that can be very helpful. Or if you put everything into one single browser window, you can still switch between the tabs. Okay, there are shortcut keys to do all of that stuff here. So anyway, this is the algorithm. The indentation has to do with it matches what we are doing inside the while loop here. So let me scroll to a portion in this code here. Alright, so once we have chosen C, so the code to choose C or choose a value for local variable C is right here. This is how we choose a particular vertex and put the identity of the vertex into variable C. And then for each neighbor n in V blah 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 such that Cn is in E, do the following. That is why we know when we choose the value of n, it is the other side of the edge going from whatever vertex that variable C is holding. That is how we can establish the connectivity of edges between the vertices, because of how the algorithm is putting values into the variables. Is that okay? Does that kind of make sense? Let me read the text channel. Yes. So each n value is a neighbor. In fact, it's a destination neighbor, because we have two kinds of neighbors. One kind of neighbor is an incoming, and the other one is outgoing. So this is for tracking the outgoing edges from C, and then locate all the neighbors that we can end up at from C. Yep. So each O being iterated on having n's as neighbors. O is different. O is only used when we are here. Okay, so only when we need to choose the next vertex that we have to take into consideration of O, and also when we have to remove it from O. But when we choose the outgoing neighbors, that has nothing to do with O. Okay, it really just has to do with what edges are connecting from the vertex in variable C. That's basically the only question. So we are only looking at all the outgoing edges from whatever vertex is in C. So that's how we can establish at least the edges. And also, once we can establish the edges, we can also establish the distances, because I'm giving you the G values. Because the G values is representing the length of the shortest path so far from the origin, where we start, to the vertex itself. And because that value is given to you, you will also know the value of the edges. Alright, so let me take a look at the text channel. So each O being iterated on has n equals to as neighbors. So each vertex that we choose from O would iterate through all of its outgoing edges where n is the neighbor. So that's kind of a more precise way to say that. And then the quote, and then the screenshot. So in the screenshot in the text channel, we can now establish, well, okay, that's not sufficient because we don't know what is C, right? You only give me what is N. So I'm assuming in this case, there's no C. I cannot tell you what edge we are talking about when there is no C. You have to tell me what C is. Oh, okay, so there we go. So when C is V2 and then N is V4, then we know there's an edge from V2 to V4. And then at that point in time, we should also know what is the G value of V2. So once we know the G value of V2 and then we know T is 21, that will also tell you the distance of the edge going from V2 to V4. Because it's, that's what T is defined, right? I mean, if you just look at how T is defined, it is G of C plus D, the distance from C to N. So that is how we can establish the edges, and we can also find out all the distances of the edges just from that portion of the trace of these of the A star algorithm. Okay, so that's good. Okay, that's fair enough. Okay, so the key here is really to understand the algorithm, okay, really well. I mean, because you need to look at the what is the trace and what is the trail being left behind by executing the algorithm, and then you look at the trail and then you're trying to reconstruct the original graph from the trail of running the algorithm. P is prev, yes. So P is basically prev, and so prev is helpful, but it's not going to be nearly as helpful. It has to be here because it is part of the algorithm, but it doesn't really help you determine the heuristic values, which is the super mysterious part is, but how do we figure out the H values, right? Because the distances, easy peasy. I mean, hoping by now you guys will feel that it is kind of easy. But the heuristic value is something else, because the heuristic value is, they're all unknown. I did not tell you anything about the heuristic value. So the question is, what clues do you get from tracing this algorithm in order to at least know something about the heuristic value? That becomes the next question. So I'm gonna let you guys think about that a little bit. So the heuristic value, you cannot know exactly what it is, but you have to be able to tell me a way to configure the H value so that the trace would look like this. There's no way for you to actually figure out the H value, but there is a way for you to at least show me and go like, okay, I think if I use these specific H values, the algorithm will explore these things, or it would choose things out of O in this particular way. Alright, so let me read the text channel. It is an underestimate, we know that for sure. Well, okay, so underestimate is not 100% right. It is not an overestimate. That's the best way to describe it. It is not overestimate because it can be exactly the same, in which case it is not under, technically speaking. Alright, so the way we can get some clue about the H value has to do with whenever we use F, okay, there's a particular, because F is including the H value, so that means, the way we choose C by saying, hey, we're going to choose the C that has the least F value of everything in O, that is how you can determine the ordering between the Fs. Once you have the ordering, and you know how each F value is supposed to be, because each F value, guess what, is really just the G value plus the heuristic, right? So once you know that those two pieces of information, one is F is just G plus H, two is the ordering, because hey, we got two vertices here. Why are we choosing V7? Well, that's because F of V7 is less than or equal to F of V3. But we already know the G values of these two vertices, so we now can say, at least in terms of the ordering, how they order to each other. So what you end up with would be a bunch of constraints of this is less than that, this is less than that, this is less than that, that is less than that, and so on and so forth. It is not necessarily a total order. it can be a partial order. But even with a partial order, you can figure out a way to assign values to the H values so that that specific partial order is satisfied without breaking the rule that you cannot overestimate an H value. So that is the last portion, which is also the most difficult portion to answer this question, is to figure out certain values of H, certain H values, so that the algorithm would behave exactly as specified in the trace. I can use a separate recording to kind of give you the details because it's kind of tedious. But here I'm just going to give you the general idea. I think it would be a good idea for you guys to try to do it first, and then watch the solution, and say, okay, is the way I do it, working or not. All right. So Wade is writing the length of the hypotenuse. I think the distance equation. No, there's nothing that says anything about these vertices being on a two-dimensional plane. So they may be set up in a way where the using the hypotenuse is not going to work. Yes, I do have the key. I do have the key to this one. Let me post it in the text channel. I did not want to post the key right away last week because I don't want people to just look at the key and go like, oh, okay, now I understand. No. With something like this, sometimes I have to look at the key and stare at it and go like, what is? Oh, right, that is, yeah. So let me put that in. This is from 1213. This is from spring semester. And it is my own fx k and a w. There we go. All right. There we go. All right. So I just posted the solution to the practice test, and of course I cannot remember what it looked like. So I'm gonna have to open it up and find out how crazy the key looks like. Alright, so I'm going to put it into the text window here. There we go. And for the first question, it really is, it's just an automatically generated thing. So it has the same kind of information, it just has a lot of words because I was programming the script to try to provide as much explanation as possible. So there you go. And then for question number 2, the comment, the slash, that is that's basically the explanation. No, I actually manually type in all of these values, just so that you guys have the highest precision when it comes to all of these numbers. Okay, next time I'm going to shorten the number of significant digits. So anyway, but for the second question, this is important. For the second question, the comment, the slash, that is not in the trace itself. That's actually my way of explaining what information you can get from the previous line or the lines that are following this. Okay, so when this is all done, you end up with all of these ordering. So so what you need to do at this point is to figure out how do I assign the H values so that all of these constraints will be satisfied. And some of these, even though it looked like a constraint, it really is not a constraint. Okay, I'll give you an example. 0 is less than infinity. That is not a constraint that you have to be concerned about, is it? It just turns out that in the algorithm, okay, I just kind of put out all the things that is known at this point. So all the things that says less than infinity probably is not something that you have to be concerned about. So you just have to worry about all the other things. Like this one is significant. This one says 14 plus the H value between V2 and V5 is less than or equal to 5 plus the H value from V3 to V5. Now that is significant because we also have this one here. Basically we have the same right hand side, but a different left-hand side. So with this, you can construct a graph. I know, yeah, to solve this, to solve a problem of a graph, you need another graph, but the second graph is not going to be complex. The second graph is representing partial ordering, like what is the largest, what is, less than or equal to that, what is less than or equal to that, and so on. So that makes it easier to solve for the actual possible values, to solve for the h values. If somebody is to give me something like this, with all the relations expressed, I would not I would not have a problem giving that person a perfect score, because once you get here, the rest is just kind of tedium to try to work out certain values to make all of these constraints met. Alrighty.
Sorry, could you repeat that last sentence?
Which one? Sorry. You mean the
Um,
ordering?
yeah, sorry, the one where you
Oh,
said
okay.
like you described like if somebody did it a certain way that you would give that person 100%, and I
Right.
my brain kind of spaced out. I didn't quite hear
Okay.
what it was.
So if somebody can give me the constraints of all the relations between these values, I would consider it solved.
Mm. Okay.
So no need to actually work out a set of value to make it work. But if
The upper limits.
not just the upper limits, because these they kind of chain, right? So if you look at let's see here, I'm just trying to pick one. Okay, so these are partially ordered because we can tell that 5 plus h of v3 v5 has to be greater than or equal to 7 plus h of v7 v5. But how that relates to other things? Oh, okay, it does. Okay, so it does chain. So we know 5 plus h of v3 v5 is less than or equal to 21 plus h of v4 v5. And so basically, you have to give me the entire relation, everything um, between all of the unknown values, so I have to be able to see all that. Is that okay? Does that kind of work out? The D's are not the
I
issues.
think so.
Yeah. So the D's are not the issues. The distance of the edges. Those we can figure out like pretty easily. The tricky part is the H values, the heuristic values in this case. And the heuristic values is it has a lot of influence to how we choose a vertex out of O to explore, and that's why the H values are they are kind of the they're kind of the life of the party. If you think about it that way, they can certainly change the how the algorithm perform the selection of the vertices. All right, so now we are. Yeah, I want to move on to question number 3. Because given the amount of time that we have, I want to finish question number 3 because that means I can now finish the entire practice exam. So question number 3, I'm just going to read the question. This is the solution, by the way, so I'm not going to continue with the solution because I do want us to be able to read the question itself and then start with that. Okay, so question 3 of 3 is we have Jana and Bobby. Each has a bag of marbles. Each bag has only red and blue marbles. Okay, so we don't have any third color, only red and blue colors. For Jana, there are 6 red and 5 blue ones, and for Bobby, there is a total of 11 marbles, in which 6 are blue, the rest are red. Okay, so from here, you can tell that, okay, so in Bobby's case, there are 6 blue marbles and then 5 red marbles, because each one can only have red or blue marbles. Jana and Bobby met Pat and realized that Pat had no marbles. Jenny and Bobby decided to donate a total of 4 marbles to Pat. Oh, Jana and Bobby also picked up a coin from the street. To do this, in order to determine, how they are going to give 4 marbles to Pat together, they flip the coin. So the way we do it is to do this, for each marble to be donated, Jenna and Bobby follow the following steps. The same coin picked up from the street is flipped, so we basically use one single coin in this case. Okay, there's only one coin that we picked up from the street, and we keep flipping that coin. Well, I shouldn't say keep flipping. We flip it exactly 4 times. If the coin lands on the head, one marble is randomly chosen from Jana's bag as a donation. If the coin lands on the tail, then one marble is randomly picked from Bobby's bag as donation. Much to the surprise of Jana and Bobby, the coin picked up from the street was loaded, and the chances of landing on the head was actually 0.35. So we can probably suspect that this was one of the lost coins from the first question. The character from the first question was Jackie. So Jackie somehow lost one coin, dropped one on the street, and then Jana and Bobby later on picked it up and go like, "Oh, we can use this to decide, who gets to give one marble to Pat in this case." That's funny. Right. So the question is, what are the chances that Pat ends up getting 2 red and 2 blue marbles? All right. So once again, the most important part is about how to set up the question, how to set up your answer. What is the first? There are 2 distinct processes, and now you have to find out what is the first process and what is the second process. And then for each process, what distribution are we using? Okay, there are only 2 or 3 distributions that we have talked about. Okay, one is really just, we are just it's just to the power of something. You have a base to the power of something, because there's a replacement of things that you have chosen out of something. The second one is binomial distribution, where each trial has 2 outcomes with replacement, and the chances of each outcome per trial is the same. And then the third one would be what I call the lotto problem, right? The lotto problem says, you were choosing something out of a collection without replacement. So the only variation that we can have is, are we counting permutations or are we counting combinations? So those are the 3 kind of distinct way of looking at something. So now we have to look at this problem and we ask, what is the first process? So I'm going to let you guys think about it a little bit. What is the first process? Just kind of imagine the story, okay, since you guys are already thinking about the cinematic universe. So you basically have these 2 characters, okay, playing something on your head. What is the first thing they have to do? Right, but what do we do to determine who is giving up a marble? Exactly, so we have to flip the coin first, okay? So we have to flip the coin to determine who is giving up a marble, and then depending on who is giving up a marble, there's a different probability of contributing a red and contributing a blue marble. So now you have to also look at the outcome of Pat ending up with 2 red and 2 blue marbles. So now you look at those 4 marbles that Pat has, and you have to ask, okay, so of those 4 marbles, how many can be coming from Jana and how many can be coming from Bob? So there are 4, let me see, 0, 1, 2, 3, 4. So there are 5 different configurations there. Alright, so let me just write it down. I'm going to jot it down in Joplin because it does get a little bit wordy if I were to verbally explain it. So I'm going to skip to question number 3 here. Alright, so there are 4 possible cases here. So now we can have 0 from Jana, 1 from Bob, and then we just make 5 cases out of these. 1, 2, 3, 4. Oops. I said 4. Nope, not 4 fours, just 4. There we go. So if 0 is coming from Jana, that means 4 is coming from Bob. 3, 2, 1, and the 0. Alright, so are we doing okay so far? at the end of the day, of the 4 marbles, there are 5 ways that Pat can be getting those marbles. Now, you also have to go back to the question and read it carefully. Is that possible? And in this case, it is possible because we have both have at least 4 marbles. Okay, because you have to be careful, because if Jenna only has 2 red marbles to begin with, then there are certain configurations that would not be possible. But in this case, every single case is possible. So with this case, okay, we have 0 coming from Jenna and 4 coming from Bob. The question is, what kind of cosmic coincidence can cause this? Okay, that Bob has to give up 4 marbles when Jenna goes like, haha, I don't have to give up a single marble. So now that becomes a binomial distribution. Okay, this is the binomial distribution portion. And the binomial distribution, I cannot remember which one is which one. So if it lands on the head, then it's coming from Jenna. If it's landing on the tail, it's coming from Bob. So in this case, we have tail, 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 because they're all coming from Bob. Okay, so now with this one, it will be tail, 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 head. This would be, oh, come on. There we go. Tail, tail, head, head. 2 tails and 2 head. Okay, the order is not important. So with this one is tail, head, head, and this one would be head, 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 head. There we go. All right, so I'm just taking a look at the text channel. Yep. All right, so yes, so Ahmad is correct. So now we have all of these where the ordering is not important. Okay, so now we immediately get to binomial distribution. So within the binomial distribution, this is the easy one because everything is coming from Bob, right? So in Bob's case, we just have to say, okay, of all the marbles of Bob's, how many ways can we have 2 red and 2 blue marbles? That would be kind of like easy peasy, right? Because we know from the initial condition here that Bob has a total of 11, 6 are blue, so 5 are red. Okay. So in this case, we basically just have to figure out exactly. We multiply those two. Okay, so we have to say we have 5 choose 2 times 6 choose 2. So that would be the number of ways that we can choose. Oh wait. This is not showing on the other side. There we go. So this is the number of ways we can have, the 4 marbles being 2 red and 2 blue, but this is only limited to the really kind of rare chance that all 4 marbles are donated by Bob. So then we have to remember that the probability of all 4 tails is according to the binomial distribution. We have 4 choose 0 because we are always relative to how many are landing on the heads. It's nice to have a consistency over here. So I'm just going to say we have 0 heads and 4 tails in this case. So that means 0.35 to the power of 0 because none is landing on the head. And then we have 1 minus 0.35, which is the chances of landing on the tail for each flip. But this one has to be raised to the power of 4. So there we go. So we look at this number, and then we have to multiply this number with the count over here, because this is representing the number of ways to choose 2 red and 2 blue marbles from Bob's. All right. So I'm taking a look at the text channel. This accounts for the loss of marbles each time Bobby gives up a marble. Exactly, because it is without replacement. It doesn't make a whole lot of sense when you say, hey Pat, here's a marble, but give it back to me so I can choose the next marble to donate to you. That doesn't seem to make sense to me, right? I mean, that's not how people donate things. You don't take it back and then redonate something. And I don't care which cinematic universe you come from. We just don't do things that way. All right, so that means the last case is also going to be easy, right? Because everything's coming from Jana. So that means, we just say, kind of the same thing. In fact, it is the same thing because in this very specific case, Jana also has 5 red and, I cannot remember. Let's see. Jana has 6 red and 5 blue, but it doesn't matter because we only want 2 from the red and 2 from the 2 red and 2 blue. So, it kind of boils down to exactly the same number here. Yep. Okay. And then the way we compute the probability is very similar to the first one, except we flip, a bunch of stuff, right? So in this case, we are having 4 choose 4 because they're all heads. Okay, whenever we flip a coin this time, every single one ends up landing on the head. So that means the 0.35 is raised to the power of 4. The 1 minus 0.35 is raised to the power of 0 in this case. Let's see. Binomial distribution is different because it is the flip side of the first one. The first one has 0 heads and 4 tails, and this one has 4 heads and 0 tails. But nonetheless, we just multiply this probability, which is from the binomial distribution, with the combination, the number of ways that we choose to from the red and 2 from the blue, and that becomes the probability of this subcase over here. These are the 2 clean cases, okay? The 3 in the middle, oh man, they are a little bit nasty. So I'm going to deal with 1, and then you guys can work out the rest, okay? Because once we talk about how to solve 1, the rest is like, oh, okay, just a little more hairy in some cases. So with this one, okay, I'm going to get rid of this line because I'm just going to copy from here because we have 3 tails and 1 head. So now we have to choose 1 as a head and then raise that probability to 1, and then the tail would be raised to the power of 3 instead of 4 because we have 3 tails in this case. But when it comes to the counting part, man, that gets a little bit kind of dirty this time, because this time we have 2 distinct possibilities, because we can have let's see here. This one has 1 coming from Jana. Okay, so now we have 2 distinct possibilities. We can say, what if Jana is contributing 0 of the red marbles, and then Bob is contributing both of the red marbles? So the one coming from Jana can be a blue or a red marble, right? So that means now we have 2 cases. So of the 2 cases, now I have to really remember which one is which one, because they both have 11 marbles and the split is 6 and 5, but it's not 6 red and 5 blue. One is 6 red and 5 blues, and the other one is exactly the opposite, which is 5 reds and 6 blues. Okay, so Jana has more red to begin with. Okay, fine. So Jana has more red to begin with, so now we will say 1 red from Jana, 1 red and 2 blue from Bob. So that is one way of giving Pat exactly 2 red and 2 blue marbles. So in this case, what is the count? How do we make this count here? Well, it's not really that difficult, because we just have to say, well, of the 1 marble that is coming from Jana, it has to be coming from the red portion. Okay, so how many ways can we do that, right? So we have to count the number of ways to do this. I think Jana has 6 reds to begin with, so of the 6, we choose 1, and I know we don't need to specify this, but I'm going to do it anyway, okay? Because this will help you with the more general case later on, is of the 5 blue ones from Jana, we're going to choose none of them, okay? So very good. So Armand is getting that idea too. And then we have to multiply, okay, C dot, to emphasize that we are multiplying with the rest. Because the other part is, okay, we need 1 red and 2 blue from Bob. So from Bob's perspective, he started up with 5 red ones, and we just need 1 of those. So 5 choose 1, but we also need 2 blue marbles from Bob, so we are now choosing 2 out of 6 in this case. So this has to be multiplied because the way Jana is choosing the one red marble is completely independent to how Bob is going to get the 1 red and the 2 blue marbles. Okay, so that's 1, and then we have to kind of do the other one, which is Jana is contributing a blue marble. Okay, so let me change the text here. 1 blue from Jana, 1 blue and 2 red from Bob. There we go. Alright, so now we just have to kind of switch the numbers a little bit here, okay? Because of the 6 red ones from Jana, we're choosing none of them. But of the 5 red ones from 5 blue ones from Jana, we're choosing one of them. And then for Bob, it is now the opposite, because now we need 2 of the red ones from Bob and 1 of the blue ones from Bob. Now in the test, if you just give me all of these expressions here, you can also assign, like variable names like x1, x2, x3, and so on. Then you can just refer to those variables and tell me how you are combining, the binomial portion with the combination portion, because you have to add up these two and then multiply that sum with this particular value, and then that product in return is one component of the final answer. So is that answering your question, Aman? You don't have to work with actual numbers. You just have to tell me how the expressions are combined to get to the final answer. Yep, there you go. All right. So I just worked out one of the 3 nastier cases. So the nastiest is the second case. Okay, the second case is the nastiest because now you have 4 things to consider, right? Because now you can say, what if, okay, let me see. You can have 1 red from each person. You can have 2 reds from one person and then 0 red from the other person. Or you can have 0 red from the first person and 2 reds from the second person. So you have 3 subcases instead of 2 subcases to consider for this case here. This one is for the most part symmetric with the first one. You just kind of have to flip the numbers a little bit. The idea is the same. It's just that the way you work out the details is a little different. Can I say that again? The possibilities? Okay, sure. So let me just write down the actual subcases. Okay, so in this case we have 1 red, 1 blue from Jana, and then 1 red, 1 blue from Bob. Right? So that's 1. The second way is to have 0 red, 2 blue from Jana, and then we have 2 red and 0 blue from Bob. And then the third one is 2 red, 0 blue from Jana, and then 0 red and 2 blue from Bob. So those are the 3 subcases. And then for each subcase, it's going to look something like this, okay? Except, the top number for each combination is going to be the same, okay? Because you're not going to change the initial ratio of red marble versus blue marble of the bags, okay? That's not going to change. But you are going to change the bottom number. How many of the red ones are we choosing how many do we want to end up with, and how many blue ones do we want to end up with. So those would be different. But it will be very similar to this one. I mean, if you okay, I can actually finish this pretty quickly too, because all it boils down to is we have to make sure that these numbers are consistent with what the text is is indicating. So 1 and 1, and then we have 0 and 2, and then 2 and 0, right? So we got 2 and 0, and then the other side is kind of the same thing, right? We just have to kind of follow the English description here. So we got 1 and 1 in this case, And then we got 2 and 0 in this case. So we got 2, and then this one is a 0, and then this is a 0, and that would be a 2. So there we go. And the only thing that's remaining is the binomial distribution in this case. So that would be, let's see here. Oh, okay. Right. Okay, so we have to kind of put that here. So this time we have 2 head and 2 tails. So that means we have 4 choose 2, because that is representing the ways of flipping the coins and having 2 heads and 2 tails, where the ordering is not important. So we have to raise the power of 0.35 to 2 because we have 2 heads, and then we also have to raise the power of 1 minus 0.35 to 2 as well because we have 2 tails in this case. So there you go. So I mean, there's only one case left, okay? Yeah, but I think you guys can figure out that one by the time we are. Yeah, by this time, I mean, you guys can figure out the remaining case because it's kind of symmetric to the first one, except you just flip the numbers. So as I said, the important part is how do we analyze the problem? How do we approach the problem, separating the 2 steps in this particular question? Now, I really have no idea what kind of question I'm going to ask in this specific final exam, but the process will still be the same, okay? Because what you need to do is to figure out how do I map the question to things that I have learned in the class. So in terms of probability and counting and stuff like that, there are really only 3 things that we have talked about, okay? One is binomial distribution, coin flipping. The second one is combination, sometimes permutation. That's from choosing something out of a collection without replacement. And then the last one is with replacement. So those are the only 3 ways of quote-unquote counting and computing probability. So the question is, which part of the question is mapping to which concept? And be able to separate those 2 and go like, okay, so this part here is binomial distribution, but once we have that, okay, this portion over here is a lotto problem, which is combination. Exactly. Yep. Overarching step, initial step is flipping the coins. In this case, finding all the ways you can constrain to flipping the coins for each way of. So for each configuration of heads and tails of the coins, then we consider all the subcases. Okay, so if Jenna ends up donating 1 and Bob ends up donating the other 3, then how many ways can we end up with 2 red and 2 blue? So that becomes the sub question. And then find probabilities for those sub things. Yes, I don't even know what term they're supposed to refer to. They're supposed to refer to these things. Now, if you look at question 1 and question 3, they are opposites of each other. Okay, because question number 1, the way we use combination versus binomial distribution is exactly opposite between these 2 questions. One uses binomial distribution first, and then for each case of the binomial distribution, we apply the lotto technique. The other one is exactly the opposite. We apply the lotto technique first to figure out the subcases, and then for each subcase we use the binomial distribution. So to prepare for the exam, okay, to prepare for these specific questions, having the ability to know what kind of a problem you're trying to solve for each step is important. All right. The possibilities are coin flip, no replacement, and with replacement. Binomial distribution is coin flip. Yep, there you go. Yep, so those are the probability things. We are out of time. So that's why we have Wednesday left. So on Wednesday we can go back and talk about the A-star algorithm, the key to the A-star algorithm that you did last week, and also the Prologue thing, the Prologue thing is it's interesting. It's on in its own way. I think the way I describe things may be a little confusing, but there are little key words that some people might be missing, and that's why step three looks confusing. No, you can go ahead and ask now. I mean, I mean, the rest of the class can go if you want to. I'm just gonna stay online because sometimes using my voice to answer questions is easier. So go ahead, Aman. You can go ahead and ask your A-star question if you don't mind. I mean, you can, if you mind, we can use direct message. So either way is fine with me. I can do it here, or I can do it over this. Okay, yeah, go ahead. Go ahead and shoot.
Yeah, I'll just use voice because it's easier to
Yep.
get the question through. So for the A-star algorithm, with this algorithm, like Dijkstra's, you're also finding like, because when I went through it, at the end I got the shortest path from A to every vertex in the graph. That's what I
With
ended up
the
with.
A-star algorithm.
Yes.
Well, that might be just coincidental.
Okay.
Yeah, that
Because
is just.
for the application we did, I did get the shortest path,
Mhm.
but I also ended up with one of the previous
Mhm.
cases. I got C to B, so then that ended up being BC.
Yeah, that is just coincidental. Now, there are several types of graphs that will end up like that. Okay, so if you think about, okay, you can think about a very degenerated graph, okay, which is just a linear thing, right? You have the source at one end of the line, and then you have the destination at the other end of the line, and then you have all the other vertices kind of sprinkled in between, but it is a straight line, right? So if you have a graph that looks like that, then after you solve for the quote unquote shortest path from the first vertex to the last vertex, then you also automatically have the shortest path from every single vertex to the destination. So that is just coincidental. Now, if you degenerate the graph, okay, where the source, where you start, and the destination are right next to each other, okay, and there's only one edge connecting those two, okay, so that you don't even have alternative paths. So in that case, you can kind of imagine that go like, oh, okay, so I just end up with one single pref, having a defined value, and that is the shortest path from the source to the destination. But none of the other vertices would have found any path to the destination. So by degenerating a graph to these extreme levels, you can kind of tell whether am I getting the shortest path from every single vertex to a destination automatically, or is it just kind of fluke because of the way this graph is configured?
So for Dijkstra's, because it like works backwards, is that the reason we can find the path from a certain start point to every vertice?
Yes. So for Dijkstra's algorithm, that's exactly why we are able to do that. It also has to do with how we terminate the loop. In Dijkstra's algorithm, we terminate the loop only when Q is empty. Well, that kind of guarantees that if there is a path from a vertex to a destination, we would have found it, and we would have found the shortest path, because of the way the values are updated. The way the L values are updated kind of guarantees that. So it's a combination of all of those things. It's a combination of how we work from the destinations back, to the other vertices in our Dijkstra's algorithm, and also the way we terminate the loop. We do not terminate the while loop until Q is empty. So we don't have a designated origin vertex and go like, oh, once I find the shortest path through this particular vertex, we're done. Nope, we do not end until there's nothing left in the set Q.
Do you mind explaining how the solution graph is defined? Because that kind of messed me up. Because the way I thought about it was if there's a element VW inside of the edge inside of the solution edges, then
Mm-hmm.
that that means that the
All right.
previous W is equal to V. I looked at it backwards instead of looking at it forwards, if that makes any sense.
Give me a second here. Let me get to the
For the
algorithm.
solution graph, do we essentially just go through the same process as drawing the normal graph, but we use the previous? function, we use the set of previous.
Right. So
Yeah, okay.
so for the A star algorithm, the prev, which is basically a function, we start with the destination. So we ask, what is the prev of the destination? Oh, okay, it's this vertex here. Then we ask, what is the prev of that vertex? So we keep asking, who is the prev, until we get to the origin, until we get to where we start off with.
Yeah, the way I saw that last line is it's just sort of like flipping around each value of the prev function.
Sort of. It is kind of switching around, except the ordering is important because we only care about. I'm trying to find my algorithm um, for A star, so I can actually point to that that thing, and it's hard to find because I got too many windows opened. So I'm gonna look for A star here and see if we can find it.
Yeah, I just posted it in the Discord if you want to take a
Oh,
look
okay.
at it.
That's quick of you. Thank you. There we go. Excellent. All right. So with the A star algorithm, the way remember in class I said the way I define the solution graph is we can do something slightly better because this one does contain some edges that does not serve any purpose because it does contain the shortest path. The way it is constructed will contain the shortest path from vertex S to vertex X, but it will also contain some other vertices where it doesn't really do anything. It's useless.
Yeah, okay.
Yeah, so it does contain the shortest path, but it's not just the shortest path that is going to be contained. So if I change the way I describe, how to construct the solution graph, which is, using using a loop starting with the destination vertex and then keep using the prev until we get back to vertex S, then it would only have the shortest path from S to X in the solution graph and without the other edges that basically they're just there, but they're not going to help us, find. It's not a part of the shortest path. Is that okay?
Yeah, I'm just like processing it.
Oh, okay. Yeah. So the way the set ESX is constructed is a superset, or I should say, it can contain edges that are not a part of the shortest path, but the shortest path is going to be there also. So we're guaranteed to have the shortest path in the solution graph. It's just that we might have some other edges that is not a part of the solution. And we got two more people typing in the text channel, so I'm gonna wait a little bit here. And by the way, did I pronounce your name correctly, Aman?
Oh yeah, you've been pronouncing it right the entire semester, so I never corrected you.
I just do not know how to pronounce it to begin with, so I just want to be respectful. Alright, so the question is, would I mind explaining question 3 of the prologue? Okay, so we can do that. Let me just kind of wait until Wade is finished typing so I can see how I want to schedule the time. But I can certainly do that. So let me...
I did have one more question about A star, but
Yeah, go ahead. No, go ahead.
Yeah, because like we're on it, and I don't know.
Yeah, go ahead.
So if we're looking at, so I was just like, these questions are based on the homework that we just had.
Mm-hmm.
So if you're looking through basically the QO, where it has like the boundaries of
Mm-hmm.
of exploration.
Yep.
The algorithm prematurely ends because basically all the estimates that we know of, which is F, they're all larger than what we've already found in G.
Yep.
And the algorithm prematurely ends. So like, but there's also like another path. See, ABD is 4, but then also ABCD is 4 as well. And I was just like thinking, if you're on like Google Maps or something and you're like looking at a freeway versus like a
Mm-hmm.
street, there could be like both those paths could be like equal, how would you be able to like? There's alternatives. In what situations would we want to choose an alternative instead, and how would we go about doing that with A star?
So A star is, and both A star and the unmodified version of Dijkstra's algorithm, both of them are supposed to only find one shortest path from the start vertex to the end vertex. I kind of modified our Dijkstra's algorithm to find a shortest path from every single vertex to a destination, but it does not find alternative shortest paths or second shortest paths and so on from the start vertex to the destination vertex. So if you want to find multiple paths, from from a particular vertex to another vertex, and just be able to say, okay, this is my first choice, but if it doesn't work out, this I want to go for my second choice, and if that doesn't work out, I want to go for my third choice, and so on. The A star algorithm does not take care of that. It does not find alternative paths. Even if two paths have exactly the same length, it will only register one of them as part of the solution. The other one is not going to be in the solution itself. So what you're asking for is a different type of algorithm where it can maintain multiple solution graphs and just go like, okay, all of these are solutions, but they are ranked in this particular way. These two are the same, this one is slightly worse than these two, and then this one is slightly worse than those two, and so on and so forth. I do not believe, well, I have not yet, seen an algorithm like that, but I would assume it would
Maybe
be
like a A star with like multiple like heuristics with a priority queue or something. I don't know.
well, with the A star algorithm. You can have multiple destinations because we just have to keep track of the heuristic value from each one to a destination. The complexity comes from, let me see, let me try to. So I'm working on this like on the fly. So I'm trying to figure out what is the complexity of it would still not be able to figure out alternative paths from a single vertex to a destination. That's the problem, because even the Dijkstra's algorithm as it is presented here does not track that. Okay, if you look at any vertex in the graph, it will only give you a shortest path from that vertex to a destination. So even if there's another path of the same length, it is still the other shortest path. It won't register it, even though it does exist. So if you want to maintain multiple parallel paths of even the same length, they're all the shortest, none of these two algorithms would track that. And I think there's a part of the problem is how we modify E prime in Dijkstra's algorithm, because the way we modify E prime in Dijkstra's algorithm is, first of all, we have this less than relationship, so we don't take care of the case when it is equal to. So that means when you find a equally short path compared to what we have at this point, it does not register the second one. It doesn't even have a chance to register because the condition of the conditional statement is false.
That answers my question. That answers my question.
Excellent.
Because I've graphed it out. I drew it on paper.
Yeah.
And their paths are equivalent.
Yep.
And, that's wonderful. But but then it just kind of defaulted to B, and I didn't know how to graph that, and so I didn't know whether or not it went along to C, and it just never updated the organization. I don't know, but
okay.
That was a question, so that makes sense. So it just kind of goes with the first one it finds.
Right, because the only update is when it finds something shorter. So if it finds something equally short, it doesn't bother to update. Now, even if you turn this less than to less than or equal to, this statement over here will basically make sure that it only maintains one of the two, because it's going to remove the edge from the other path. So even if you find a path of equal length, the path of the first one, the first path of that length is going to be lost because we remove that edge. We remove those edges. Alright, so I'm just reading the text channel. In the middle of a satellite navigation path finding, there's a nuclear explosion. Yeah, finding alternative paths is actually very important. So if you think about routing, okay, so think about networking, okay. Um, if you look at a router, has a routing table and go like, okay, for this packet here, it's supposed to end up at that IP address. So which other router should I route this particular packet to? So if you think about it that way, it is a shortest path kind of problem too. So the question is, what if one of those routers along the way, is broken? Then, so that would basically change the distance of the edges right away, because certain routers would now be unreachable, or the distance would become a very high value. So one way to take care of that specific problem is a dynamic update of the distance of the edges, and you just basically have to recompute the shortest paths of the vertices in that case. But being able to figure out alternative paths is important. But so in the case of Google, for instance, okay, so in the case of Google navigation, if let's just say that there are a lot of people going from point A to point B, so you don't want to direct everybody to use the same path until that path is saturated, and then you direct everybody to go to the alternative path, because that you're just basically you're just switching between several paths, and every single time you pick one, you're flooding that path with with all the traffic. So it makes a whole lot more sense by saying, okay, we're going to do this in a probabilistic way. Okay, the first path A is good, path B is almost just as good. So I'm just gonna say, okay, I will send, just randomly, I'll send one half of the traffic through the first path, and gonna send the other cars, through the second path. So this way you're also handling load balancing, between the paths. So I think at that point you're no longer looking at algorithms as simple as A star or Dijkstra's algorithm. You'll be looking at something that is, I would say, a bit more complex, and there'll be a lot more stuff that you need to maintain and dynamically update at the same time.
I have a question about that,
Yeah,
actually.
go ahead.
So, like, let's say, just in the terms that you were talking about, what
Mhm.
would we call an A star which doesn't check to see if, like, once it's found a path,
hmm
it immediately ceases. It doesn't look for a potentially shorter path. It just goes for the first one it finds. What would that be?
Um,
Dijkstra's? No, it's not Dijkstra's.
no, Dijkstra's is the way Dijkstra's works is it does find the shortest path. So greedy is referring to what people call greedy, I call optimistic. It's just how we choose the next thing to expand. So okay, let me pinpoint where I would say is making this particular algorithm optimistic. So this part here is why this algorithm is optimistic, because it's looking through all the vertices in O. In other words, it's looking at quote unquote the frontier of all the vertices that just got their G value updated. Okay, so looking through all of those and go like, which one should I pick to expand? And it's being optimistic and go like, let's pick the one that has the least value. So that is the optimistic part of this algorithm. So greedy algorithms tend to find the shortest path, tends to find the optimal solution. That's, I know it's counterintuitive, but being greedy in terms of algorithm, usually would end up finding the optimal path. Oh,
It
okay.
just may take a lot longer or cost more
Correct.
energy.
Yeah,
Yeah.
it can. Yeah, so if you assign the heuristic value in a way to try to make the algorithm go through more iterations, you can do so. Okay, so you can basically hand pick each values, just so that you're tricking the A star algorithm to explore more things that otherwise would not be necessary. In other words, you can choose H values to make the A star algorithm perform worse than Dijkstra's algorithm, because Dijkstra's algorithm is what we call an uninformed search algorithm, because the heuristic function is basically an information to help guide the search algorithm to kind of point it to the generally correct direction, just kind of go over there. Okay, that's likely where the solution is. That's what the H value is supposed to do. But you can't handpick your H values to make it do exactly the opposite. Is to try to trick the algorithm. But the way the algorithms are constructed is, as long as your H values do not overestimate, it will still find the shortest path. So is that okay so far?
Yeah. I think that helps me figure it out. So it's kind of just okay. Yeah, I think I got it.
Yeah, so from the questions that you guys are asking, I'm really glad that you guys are asking these questions, because that means you have been actually spending time to experiment with the algorithms and try to figure out what each step is really meant to do in the context of finding the shortest path. And that is the kind of studying that I think people should be doing. Is not really just to read the text here and go like, yeah, I kind of understand mechanically what it's doing, but do you understand how each statement relate to other statements, and why we end up finding the shortest path the way we construct the algorithm like this? That is a deeper level type of studying, and I think that is really crucial. Not so much in this class, because this class is really just equivalent to a lower division class at a 4-year university. But when you get to the upper division version of this class, and there are at least 2 or 3 of them, then the usual shallow studying technique is not going to work in those other classes. So there's that. So
Thank you.
Yeah, absolutely. Well, thank you. So let me get back to On's question. And am I pronouncing your first name correctly? On. Okay. All right. So let's go to that question. And if Wade or Aman has additional questions, don't hesitate to kind of queue it up in the text channel. All right. So question number 3, I believe, is this one. So is that the correct one that you want me to go over? An nth cousin is not just a person with a common n plus 1th, n, yeah, I'm not even sure how to pronounce it, because it's n plus 1th ancestor, but there should be no common ancestor in between. Okay, so I got a question from someone, not presently in the text in the voice channel, but someone asked me that question. It's like, how can these 2 people not have a common ancestor when they are supposed to be cousins? Well, that person forgot that no common ancestor in between. Okay, so between the n plus first, I guess that's one way to pronounce this, ancestor, and these individuals, there should be no other common ancestors. So that's kind of what this keyword here is really important. Is that kind of the question that you want me to address on? I can keep reading it. Make another copy of the program. Okay, so that's just cloning, and then you just add one more function. This means it's important to look for common ancestry closer than what is needed. For example, in the case of 2 second cousins, we need to make sure that they do not share parents or grandparents. This gets a little more complicated than we take n times removed into consideration. If x is a 4th cousin twice removed of y, that means the intended common ancestor is 5 parents away from x and 3 parents away from y, but x and y should not share any ancestor prior to the 5th and 3rd ancestor, respectively. So it's basically the same individual, but that individual is the 5th ancestor or 5th level ancestor of x and 3rd level ancestor from y, and there should be no other common ancestor between these 2 individuals and the ancestor. That's basically what this means. So I'm not sure whether I am addressing the question or not. I cannot hear you on. Even though your mic is unmuted, I cannot hear you. Just in case On is asking questions with the voice. What is the link to that Simpson chart? Oh, okay, I can do that. I just got it up and running today, so I can look for it. For someone like me, this is really helpful. It is a way to search. I believe just the tab or the text of the title of a page. But it comes in super duper handy, and I'll copy the link into the text channel just so that people can find it. There we go. Yeah, but you can go ahead and type your question if your voice is not working. There we go. And the focus is, I think the portion that is easier for us to test with is to figure out between BART and we can go for let's see here, Pomona, or we can look up Furnace, or we can look up Twila, because all of these are individuals who are cousins of Bart, but with various times removed. And because they trace their ancestry all the way up to, I think Howland is the one. Yep. So Howland Simpson is the common ancestor that we are working with here, and then we have Otut, and then we have Twila, and so on. Okay, let me get back to the text channel. Yeah, my cats would do the same thing. For whatever strange reason, they know which function key to press to turn off Wi-Fi. So at least yours is not turning off your Wi-Fi, just turn off your mic. Cats are little evil creatures, but we love them because they're evil. Yeah, just think about all the cat hair, blocking the heatsink of a computer. Alrighty. But am I addressing the question? Yeah, go ahead.
No, you triggered me. Oh my god, I have one of my old towers wrapped up in a trash bag. It's so covered in hair. It's wrapped up in because it's it's out of date, but it's wrapped up in a trash bag because there's so much dust and cat hair stuck to it. Oh my gosh, cat hair is the worst.
Yep, especially those with fine hair. I have two short hair cats, but they have really fine hair. One sheds a lot, the other one does not. So I just have to constantly use a blower. I have a compressor, and an air gun. So I just, kind of blow the dust out, blow all the fur out. So that's just a part of the routine these days. Yeah, air cans are dangerous. Okay, so Amand, air cans, they use a chemical that is actually toxic. So if you use the air cans, I'm assuming you're using the chemical air cans, not the electric ones. You have to be super careful because the mask is not going to help with the toxic chemical in the air cans. Yeah, if you read the labels carefully, they would say that you have to use it in a well-ventilated area, which kind of begs the question of, what if I don't, right? What if I'm in a very confined area, like inside a car, and I'm trying to blow the dust off my stuff? As it turns out, people can die from it. Some people, do not die, but they probably wish they did because it would destroy the organs. I think it would destroy your internal organs because they are kind of toxic. So I do not use air cans anymore. I use electric blowers. So I have an electric blower, which is kind of like a hair dryer, but without the heating element. And then the other one is just a compressor. Go to Harbor Freight, spend I think like $40 or something like that. Pick up a compressor and just get a little pointy thing, so you can direct, the compressed air where it goes. That is a lot safer because it's just regular air that you breathe.
Like
But
a
yeah,
compressor. I have a question about the compressor, by the way, because I've thought about this.
yeah, uh-huh.
I've worried that by using the compressor, that something about the velocity of the air might statically charge the computer components. I don't know. Is there anything to worry about that? Like, blowing dust so hard that it damages components. I don't know.
Okay, I got to tell you this funny story. I was Yeah, I know we're shooting the breeze right now, so if you guys want to kind of not hang out with us, that's totally fine because this is just kind of us shooting the breeze. Um, so I was cleaning my son's computer, and he's the one with the with uh with a GPU, because I don't game much, and I have a laptop computer. So he has a GPU. The GPU has a fan. So I was kind of blowing the dust, out of that fan. And then after that, my son said, hey, the computer's making these kind of rattling noises. Go like, oh man, why is it like that? So at first I thought, maybe when I put it back together, I did not put in the screws, correctly, and it's just not tight enough. But sure enough, it has to do with one of the fans. So later on, I took out, all the components. I think he got a I had to replace one of the components of the computer. But when I took it out, I saw one of the blades of the fan missing. And that's from me, kind of blowing the dust. So I think what happened was I blew the air through, so the fan was turning really fast, and then accidentally the tip of the blower, physically contacted the one of the blades, and it just broke off. So I found a replacement, put it back in, and everything is really smooth and balanced, at this point. So you just have to be careful not to not to blow it too hard, to so that the fan spins so hard, so fast that it causes some damages. Um,
Yeah, that's maybe get a diffusing nozzle or something. But that's really funny.
yeah, it is funny, but I have not heard of the static problem.
Mm,
There are a few reasons why you won't have a static problem. Um, the nozzle thing is metallic. So as long
mm,
as you are sitting on the ground somewhere, you have that grounding effect. So the static charge is not gonna be there. Um, and air itself is not going to be charged to begin with. So if you're worrying about the friction between air and the components of your computer and that potentially building a charge, I don't think that would be a big concern. I really don't think I've heard of cases
mhm.
where that is a concern. The chances of physically damaging a fan is much higher compared to
Yeah.
electrostatic discharge. There we go, ESD. Um, so the key to not to blow it too hard is a lot of compressors these days, even from Harbor Freight, they have a regulator. So you can basically
Mm,
control the air pressure coming out of it. So even though the tank pressure can be 100 or 120 psi, that's the usual set point of the compressor, the output can be down to like 30 psi, or whatever safe setting that you want to kind of use. Because all you have to do is to kind of start low and then start blowing the dust until you get to like, okay, I need a little bit more strength. I need a little bit more volume or airflow, so you can crank it up gradually until you get to the point where it gets the job done, and then you can just turn off the set point of the regulator, so that way the outcoming air is not going to be too fast.
I'm gonna get a compressor. Thank you.
Yeah, they're kind of
I
big. They kind of take up some
yeah,
space, but I think they're a lot safer, chemically speaking. They're a lot safer compared to the air cans.
and you can always fill them up, and then unplug them, can't you?
Yes, you can. Um,
Yeah,
once
the
you
smaller one.
Yeah, so the tank that comes with these compressors, they have a certain volume. The small ones are only
Hmm.
about a gallon, in terms of volume. It doesn't last you very long. I mean,
Yeah,
you can pre-compress and then carry that thing around, but it's not gonna
you're gonna
last
have to
very long.
refill pretty soon. Yeah.
Yeah. So I would just kind of take the whole thing and just
plug
it's
it
a
in
little,
wherever you're working with it. Yeah.
yeah, it's a little bit on the heavy side, but it's not that bad. I would say about the same weight as
It's
a.
really that's cool. Um I'm really into the crafting
Hmm.
community online. So uh compressors, you use them for vacuum pumping and for pressure casting for resins and silicones.
Oh, right.
Yeah, so like I've kind of wanted to try because that gives me a reason to, you know, have have a compressor, but also start buying rubber. Um, but I've been worried about buying it, so this was helpful. Thank you.
Yeah, yeah. So if you go to Harbor Freight and look for compressors, they used to be really loud. I mean, these things, when you
Mm,
turn it on, they're pretty loud because they have a piston. That's how they compress the air. Is they have a
hmm.
piston. It's kind of like the reverse of a car engine. Instead of using the pressurized, gas to work to translate to mechanical work, they're exactly reversing the whole process, right? They're using the mechanical rotation of the motor to compress air, but that makes it really loud. The new
Hmm.
ones, they're really quiet because they have quote unquote mufflers, and the mufflers really work. I mean, because I got one, and once it's an extra part that you kind of put onto the air compressor, and once you
Hmm.
put it on, it kind of hums a little bit, but nothing even close to a hair dryer.
Oh wow.
Yeah. Oh, these things are they're really quiet, and plus it's a kind of low hum. It's kind of like
Yeah,
that. Yeah.
like almost
Instead
like a
of
refrigerator. Oh, it's a refrigerator. Yeah,
um.
because there's a compressor pump in all
Yeah.
AC cooling.
Yeah.
Oh, okay, cool.
Yeah. But those are different because they do not
Those,
open
yeah,
to atmosphere. These
yeah.
open up to atmosphere, and that's why they can be
They're
noisy
loud.
because the
Oh,
piston.
sorry. He has
Yeah.
a question. They
Yeah.
have a question.
All right. So Owen
Please don't
has a
forget. Okay.
question. What question is that? I thought I answered that question. Okay, go ahead.
Oh yeah, you have a question. Sorry.
Well, I thought I answered that question, but maybe not. All right. From the picture. Oh, from The Simpsons? The ancestry tree of The Simpsons? Oh, okay, sure. Let me get back to it. Nope, not that one. Still not that one. Where did I put it? Oh, this one, I think. There we go. All right, so within this picture, if you put in all the parent-child relationship, I would put in um, Bart, Lisa, Maggie. Just pick one of them. Okay, I would pick two because you want to make sure that siblings do not get mistaken as cousins. I would put in Homer. I would put in Abe. I would put in Orville. I would put in let's see, who's Orville's ancestor in this tree, in the tree that I care about. So Orville, and then Otut, and then Howland. And then from Howland, I would go down to Twyla or Twyla, and then from there go to Furnace, and then from there get to Pomona, and then from Pomona you want to get to Alberta, Hazel, and Violet. So that would be the sub tree that I think is going to be applicable. Okay, great. So now the first thing you can test would be just regular nth cousins, right? So the question is, how does Bart relate to Alberta? So you have to count the number of parents until you get to the common ancestor. So I think they're fifth levels, right? Fourth cousins, exactly. So there are five parent levels before they get to a common ancestor, and that's why they're fourth cousins. So you have to be careful because you want to make sure that Lisa is not considered a fifth cousin, a fourth cousin of Bart also. Because obviously these two, being siblings, they also share ancestry all the way along, right? Homer is a common ancestor. Abe is a common ancestor. Orville is a common ancestor. Olstad is a common ancestor. And then finally, Howland is a common ancestor. So on one hand, you can say, Bart and Lisa, they share Howland as a common ancestor. This is 5 parent levels away. But at the same time, Bart and Lisa are not they are not fourth cousins, because they also have earlier, quote unquote earlier, parent, shared, parents or shared ancestors. So that is why that's why I said, do not have any common ancestor between the people that you're trying to establish cousinship, and the one common ancestor at the right level. So in this case, the right level, when you want to test it, you want to use Howland, which is all the way over here, as the common ancestor. So from that perspective, Hazel and Bart would be proper fourth cousins. But between Bart and Lisa, they are not. They should not be considered fourth cousins, because they share ancestry before we get to the 5th level parent from the family tree. Does that kind of answer the question?
Where was Hazel again? Sorry.
Hazel is all the way here. So Hazel is a 4th cousin of Bart. So ancestry X, Y, and M is true. It should not be true for Bart and Lisa. I'm not. Let me think. You need to create another one. Okay, so I think ancestry X, Y, and M is supposed to be false between Bart and Lisa. But in order to do that, you need another predicate that really just says, okay, between this person and this person, do they share a common ancestor at that level? Even if there are earlier ancestors before that ancestry level, it will still return true. So you need some ancestry predicate that is that doesn't enforce that this is the minimum level before we get to the common ancestor. So let me just read my own description first, because sometimes I write one thing and then I forget what I wrote. Let's see, not this one. There we go. Alright, so let me just read this again. Okay, what to do? You need to think about a new predicate. There we go. So you need a new predicate, because ancestry X, Y, and M should exclude. Okay, if you put in Bart and Lisa over here, and then 4 and 4 over here, they should not be. It should return false, because they are not 4th cousins, or 5, 5 I should say, because N and M count a number of ancestry, number of parent links before we get to a common ancestor. So if you have Bart, Lisa, 5, 5, that should return false. If you put in Bart, Lisa, 4, 4, that should be false too. 3, 3 should be false. 2, 2 should be false. 1, 1 is the one that should be true, because they share Homer as a parent. Okay, I'm reading the text channel. Common ancestor XY can be parent of an ancestry XY and M. Right. So common ancestry still requires they require the numbers, I think. Let me double check here. So you need to use negation to get this part done, because of the exclusion of earlier ancestors. So you will also need to use comparison greater than and so on. So so the new predicate also needs to count, because you need to make sure that the common ancestry does not occur at a lower level, at a level that is lower than what you need. So it's not just checking whether they share a common ancestor, you also need to keep track of how many parent links away that ancestor is. Yep. Alright, so there you go. So basically the common ancestor thing is like ancestry XYNM, except it does not have the extra requirement of, X has to be N away from the common ancestor, and Y has to be M away from the common ancestor. Yep, sure, you're welcome. And Wade just said, "Oh,
I really thought about it in terms of genetics, and it made more sense. Like
oh,
Mendeleev squares.
sorry, say that again."
Mendelian squares? No.
I'm not familiar.
AB crossed with AB, right? You have
Oh,
A, and then the last one is BB, right?
uh,
So anyways, so I started thinking about it like that, and okay, if two individuals, right?
mm-hmm,
If if they're related,
mm-hmm,
right? So if they're related, that's checked for. Because if you're not related at all, it doesn't matter. So it checks if you're related, and if you are, that's good. But between the two of you, there must be an ancestor which you two do not share, right? Because otherwise, two grandchildren will be will have the same grandparents if they are blood related.
right. Yeah,
Yeah,
so
so it has to be not that. Yeah.
right. So if you go to the graph, I'm not sure that we have an example like that here.
I mean, Lisa and oh yeah, like so if you look at like Zeke Hickman on the right above Penelope Olsen, right? So he's a new addition into the family on Bart, Homer, and Marge. Yes, so he's a new addition to the family. Um, so every new addition on the family on this tree,
Mm-hmm.
both Lisa and Bart share, right? But if you look at someone on the other tree, like Alberta, you go up to Pomona, right? They
Mm-hmm.
don't share. If you look at Alberta, right, they at somewhere up the tree,
Mm-hmm.
they share one ancestor, but the other ancestor out of the mating pair, they don't share.
Correct.
Yeah. Okay. Cool. I
Yeah.
got it.
Yeah, so the key is, between Alberta and Bart, the
Hmm.
first shared ancestor is um, Howland. I think Howland is the
Yeah.
first shared ancestor. So that's why they are quote unquote proper fourth cousins, because they do not share any ancestor prior to Howland.
Yeah. Cool.
So
All right.
yeah, the other way to look at this is easy. The other way to look at this is, even though Howland has a parent of Garwood, so um, so that means even though Bart and Alberta, even though they do share a sixth level parent or grandparent, um, they are not fifth cousins. They're only fourth cousins, because
Mm,
the first, if you go up the family tree, the first shared ancestor is 5 levels away, which makes them fourth cousins.
I see.
Yep.
Cool. All right. All right. Thank you very much.
Yep. You're welcome. All right.
I think this has answered my question perfectly.
All right. Excellent.
All right. See you Wednesday.
Yep. See you on Wednesday. Have a good night.
You too. Thank
Hmm.
you very much.
All right. Hmm.